My name is Heather Cegla and I'm from the University of Warwick. I've been tasked today to talk to you about the various sources of stellar variability that you might see manifesting in your exoplanet data. So to make sure we're all on the same page, let's refresh ourselves and think about what does that exoplanet data actually look like. Okay, so we've got a star-planet system. They're gravitationally bound to one another. That means they share a common center of mass. And so both the star and the planet are wobbling about that center of mass. And as the star wobbles away from us, we see that light as being redshifted. And as the star wobbles towards us, that light is in turn then blue shifted. And so if we study the star itself, we can infer the presence of the planetary companion. And the main reason that we want to study the planet or the star itself is because the star is far more luminous than the planet. So it's much easier to infer the presence of the planet by looking at how the star changes. So the example I'm showing you here on the right is from 51 Pegasi b. This is the classic exoplanet example because it is the first planet we found outside of our solar system around a sun-like star. So you see on the y-axis you have the velocity of about plus and minus 100 meters per second. And on the x-axis you have the orbital phase. And you can see the sinusoid that comes up here. For more information on why that Doppler shift arises and how we measure it and how the instruments work and how to infer what the mass is from these signals, go ahead and check out these various talks I've listed here. You can get a really good deep dive from all of these and they'll be listed on YouTube in the same way that this one is. So let's go back to 51 Peg. All right, we have our sinusoid here. This is our planetary signal. Now let's zoom in on this area here, around plus and minus 6 meters per second. And the reason I'm zooming in on this is because what I'm interested in now is pushing beyond the previous detection. So 51 Peg B is a hot Jupiter. But the next step, now that the instruments have improved, is to try to find a true Earth analog. And the signal of an Earth twin is what I'm showing you here in red. So now we really want to zoom in a little bit more so you can actually see that sort of sinusoid shape there. And the signal from an Earth twin is a mere 9 centimeters per second. So you can see how this would have really been hidden in that instrumental noise. If you look at the error bars in that left-hand plot, they're really much larger. But now we've got to the point where the instruments are improving and what we're being dominated by instead is the variability from the stellar surface. So what I'm showing you here in yellow is data from the Harps North Solar Telescope. So this is what it would look like if we tried to find an Earth analog around a true solar twin. You would have all of this variability, all of these velocity shifts in yellow coming from the star itself, and they would completely swamp the signal that you get from an Earth analog. And the reason for that is because our sun and the sun-like stars are not homogeneous. They have all these different inhomogeneities, and it's not a static sphere. It's constantly evolving and changing. And so now we're at a point that we really need to understand the variability and the physics that is happening on the surface of the star so that we can disentangle and pull out that Earth analog Doppler wobble. So let's go back to the sun. Here's the various components of the sun sort of broken down. And what we're going to be focusing on here is the stellar photosphere, because the stellar photosphere is the surface of the sun. This is where most of the starlight is coming from when we're measuring the data, if we're using a spectrograph that is operating in the visible light. So let's break down that photosphere or that stellar surface a bit more. So this is a really nice image from Tim Milborn, where he's divided up various components of the surface of our sun based on the brightness and the magnetic field. So you have in blue the quiet sun. That's your sort of standard photosphere where we would normally think it's pretty homogeneous, but I'll show you later on in this talk about all the different inhomogeneities that are actually present there. And in between all of the blue things, you see lots of little white veins. That's the network. And these are magnetic field lines weaving through those, and we'll kind of talk you through those as well. And then on top of that, you see in yellow what we would call plage or faculae. And these are a magnetic region that you see quite evenly spread out all over the surface of the sun here, and particularly surrounding the spots, which you see highlighted here in orange, which are dark bits that we'll talk through. So this is just kind of a global view of what the surface of our sun looks like and what most sun-like stars are going to be looking like. So let's dive into that stellar surface, which we called the quiet sun. So I'm showing you here an image of the quiet sun at the center from the Decazed Solar Observatory. It's a really pretty incredible high resolution image here, where you have the surface area that you're seeing is about 30 by 30 megameters. And you have these individual granules or hot bubbles of gas. And because they're hot bubbles of gas and you have convection happening, they're going to the surface of the sun, rising up and being blue shifted, cooling, and then falling back down and being red shifted. And you will see that the granules, those bubbles of gas, not only are they brighter, but they're also a lot bigger. So because they're coming towards us, that means altogether we end up having a net blue shift. And so these individual granules are moving at about a few kilometers per second. And you would think, whoa, that is way bigger than our 9 centimeter per second signal. But of course, we have some upflows and some downflows. So there's going to be a lot of canceling. And for our sun, there are about 10 to the 6 granules that are visible. So there's a lot of canceling, but not everything cancels. And you end up getting a net variability on the several tens of centimeters per second, which does completely swamp what we would deem to be an Earth twin. One other thing I want to point out on this is you see these sort of bright regions that are in between the granules. Those are magnetic bright points, and we'll come back to those. So the key takeaway here is you have your hot bubbles of gas, the granules, rising to the surface, being blue shifted, cooling and falling back down and being red shifted, which you can see in that schematic in the bottom right-hand corner. And not only do we have that sort of temporal variability, we have a center to limb effect as well. So what I'm showing you here is some 3D simulations of the sun where you go from this center to the limb. So because you have these hot bubbles of gas that are rising and falling back down, the surface is actually corrugated. And a good analogy is to think of it as sort of hills and valleys. When you're looking at this center, you have sort of a bird's eye view. And you're looking into the very bottoms of the valleys, and you see the very tops of the mountains or the hills. But as you look towards the limb, then you can no longer see to the bottoms of those valleys. And you begin to see actually some of the valley walls, or the granular walls in this case. So you have different line of sight effects. So that's both manifests in brightness variations as well as velocity variations, because you would have these horizontal flows at this center that would be perpendicular to your line of sight and therefore not contribute anything to the velocity that you're measuring. But as you go towards the limb, those horizontal flows now are not completely horizontal, and you get a line of sight, you get a component of velocity along your line of sight. And so there are both temporal changes as well as center to limb changes. So how does that impact our velocities? Well, let's refresh ourselves of how these velocities are measured. So I'm showing you here an example of a stellar spectrum where you have your absorption lines where the starlight is being absorbed. And we cross-correlate that with a template mask. And that gives you sort of a super precision, which manifests as your cross-correlation function. And we tend to measure the centroid of that, usually using a Gaussian to determine what that centroid is. And that is what we would call the center of mass, or the velocity shift there. So you can imagine, if you have a Doppler shift, that's a wholesale shift in that cross-correlation function, because all of those stellar lines are moving. However, if you have any sort of asymmetries present, then if you go to measure the center of light, you could end up having a spurious velocity shift, where there's not actually a Doppler shift, but it looks like one just because the line is asymmetric. So to break that down a little bit more, let's take our line profile that we have in gray and let's break it down into the various components of granulation. So this is a really simplified point of view here, thinking only of the granules upflows and the intergranular downflows, but it's a bit more complex than this in reality. But this will give you an idea of where those asymmetries arise. So you have your brighter granules, so they've got the higher continuum intensity, and you can see that they're more blue shifted compared to the intergranular lane. And now they make this profile asymmetric. And one way to measure the asymmetry is to look at the bisector. So we measure the bisector by taking horizontal slices and then grabbing the midpoint of those slices. And if you had a perfectly symmetric line, you would have then a very straight bisector. However, if you zoom in on this one, because this schematic is based off real solar observations, well, actually real solar simulations, then you can see that there's this characteristic C shape. And this is because the simulation is from the sun. And so as I move my cursor here, you can see that the granules are contributing to this sort of blueward trend here, and the intergranular lanes are sort of contributing to this sort of downward trend here. And as the granules continue to evolve and change, and the amount of granular to intergranular lane changes, then this sort of C shape sort of bends like this and changes, and it'll move this way and that way depending on that ratio. So the key takeaways here is the convection, also known as granulation. It introduces asymmetries. So no matter what, if you have a convective envelope, you are going to have asymmetric line profiles and therefore an asymmetric cross-correlation function. And if you are looking at something like the sun, you're going to have a net blue shift because of the ratio between the granules and intergranular lanes. And you're going to have temporal velocity shifts of several tens of centimeters per second. And to really hit this home of what those temporal velocity shifts look like, I'm showing you a model star based on the backbone is 3D magnetohydrodynamic simulations, where you have an individual iron line profile here, where you have flux on the y-axis and the wavelength on the x-axis. And that bisector is shown again here in red, but it's zoomed in by a factor of about 30. And it still looks like it's static. You can see that it shouldn't be static by looking at the model star in yellow, because it's twinkling to sort of illustrate the changes in the granulation filling factor. So if we really zoom in on that bisector by a factor of about 10,000, then you can see that it's moving at the plus and minus several tens of centimeters per second here. And this would be happening on timescales of a few minutes, because an individual granule lives for about 5 minutes. So you might think, because an individual granule has such a short lifetime, that we might be able to just average or bin this out. For example, we often have to take exposures that are 5 minutes or more in order to have the signal to noise to get the precise enough radial velocities to measure those planets that we're looking for. However, the granulation doesn't really average out very well. What I'm showing you here is some images from the sun, from the Dunn Solar Telescope. A single exposure is shown in the bottom right-hand corner. And then all the other ones are 1 hour time averages. And you can see that even after you've averaged for over an hour, you can still really make out the structure of the granulation. And part of that is because the granules tend to appear and disappear in the same locations. So this sort of signal or noise, if you will, is quite correlated. And one of the reasons for that is because that magnetic field kind of weaves in between those granules, sort of holding them into place. And so that's one thing I really want to stress here. Anytime you hear someone talking about convection or granulation, shown here with some simulations of the continuum intensity or brightness, they really mean magnetoconvection, because the convection always interplays with the magnetic field, and the magnetic field is inherent to the star itself. And you can see it, as I mentioned before, weaving in between those granules, and you can have strengths of a few kilogauss here. Unfortunately, I don't have time today to talk about all the really cool ideas that we have about how magnetic fields are generated and maintained, but to learn more about the dynamo mechanism that may be operating on our sun or sun-like stars, I'd recommend you go ahead and check out these review papers. So the takeaways when it comes to convection and granulation is that individual lifetimes are a few minutes, maybe up to 10 minutes, depending on which star you're looking at. Individual granules move at a few kilometers per second velocities, but a lot of this up and down motion cancels out, so you have a net effect of several tens of centimeters per second. For the sun, it's probably close to 40 or 50 centimeters per second. And this net radial velocity effect decreases for cooler stars and increases for hotter stars and for evolved stars. For example, if you go and try to observe at an M dwarf, you're going to have a lot less contrast variation between the granules and the intergranular lanes, and the flow speeds are going to be decreased. So the overall effect means you're going to have less variability in your radial velocities due to the convection on M stars. In addition to that, if you were trying to find a rocky temperate planet around an M star, because that star is cooler, that temperate zone is closer to the star, so then your Doppler wobble is larger. So combined, it really means if you go towards those cooler stars, this is not really going to be a dominating effect in your radial velocities. But as you go towards hotter stars, and you were to say look at a G star like our sun, and you were trying to pull out an Earth twin, this is something that you're really going to care about. And overall, most, if not all, of the stellar variability is governed by this interplay between the convection and the magnetic fields. So even if we don't care about the small scale granulation, we care about the physics of the convection and how it interacts with the magnetic field on a larger scale. And I'll touch back onto that as we continue along in this talk. So I mentioned the small scale granulation. In addition to that, we have a larger scale of granulation, which we call supergranulation. I'm showing you here a Dopplergram from SOHO, so you can see the blue shifts and red shifts from the supergranules. And the reason why you can make them out so well is because the supergranules are actually quite large. And what they are is actually collections of individual granules grouped together with a diameter of about 30 megameters. So you can see here in this schematic of supergranulation how large the diameter is, and in between individual supergranules, you'll see sort of magnetic bright points and this clustering of the magnetic network that I mentioned earlier. And you have horizontal outflows from these supergranules of about 300 meters per second. And you might again think like, whoa, that's a huge velocity shift, and would completely swamp a low mass long period planetary signal if you were trying to pull it out. But it's important to keep in mind the fact that the contrast of the supergranules is not very large. So it doesn't manifest that much in our data. And in addition to that, these are largely horizontal flows, which means when they're at disk center, because they're horizontal, they're perpendicular to our line of sight. So they don't contribute to the velocities that we're measuring. It's only the supergranules as you start to go away from that where we start to pull up some of those line of sight components and to measure those velocities. So the net effect ends up being around the 1 or 2 meter per second scale, at least for the sun. The sun is the only place where we can really spatially resolve these, and it's the only place where we've really studied supergranulation. You can possibly try to pull it out in terms of this power spectrum of looking at different stars, but if you want a direct detection, the sun is still going to be your best place to explore. So to sum up, you have collections of granules at about 30 megameters in diameter, and the velocity flows are horizontal and about 300 meters per second. You do have some vertical flows, but they're really quite reduced. But the net effect overall we're looking about here is around 1 meter per second or so. And we really need to study this a lot more to understand the best way to mitigate and remove this signal. Another key thing to keep in mind is the time scale we're looking at here. For the sun, the lifetime of an individual supergranule is around 1.8 days. So that's kind of the scale that we're looking at if we're trying to find solar twins. There is another type of granulation that is talked about as at an intermediate scale, which is mesogranulation. However, it is quite hotly debated as to whether or not mesogranulation, one, exists at all, or B, exists and is a true type of convection. For me, and my understanding based on these solar reviews here from looking at supergranulation and collecting a lot of the literature here, it's really quite likely that mesogranulation is a ghost feature of surface convection generated by averaging procedures. So you might see a signal there, but it's probably not a true signal of convection. It's probably not true physics that we're looking at here. And the latest stuff that we have is these really nice high resolution space-based observations from the Solar Dynamics Observatory. and they show a lack of a distinctive spectral feature at that sort of mesogranular timescale. But again, the jury may still be out here because there's still some who are arguing that this is still a distinct signal. So I wouldn't count it out completely, but in terms of the physics, I would really focus mostly on understanding granulation and supergranulation foremost. So this convection then leads us naturally to looking at these pressure mode oscillations. And the reason for that is because it's the convection, the movement of those hot bubbles of gas, that actually excite these pressure mode oscillations, which you can think of as acoustic modes. So our sun and sun-like stars are essentially ringing like a bell at a particular frequency. And that means the surface of the star is sort of moving in and out. And because the surface of the star is moving in and out, we then get a Doppler shift that corresponds to that. For our sun, this is on a couple meters per second. So this is some Bison solar data that I'm showing you here. So on the y-axis is your radial velocity of plus or minus 5 meters per second. And on the x-axis, you have time going up to about 300 minutes. And if you look carefully, you can see that our sun rings with a pretty consistent frequency at about 5 minutes. There is some variability in here because it's quasi-periodic and because what you're seeing here is the manifestation of both the granulation and the oscillations here. To think of it in terms of the power spectra, so that's what I'm showing you here, where you have the power density on the y-axis and the frequency on the x-axis, you can see that the oscillations really operate over sort of a finite frequency range. And whereas the granulation, because here it's both granulation and supergranulation, you have it over a much longer frequency space. So you can see, even just by looking here, the granulation is going to be quite difficult to bin out, whereas the oscillations, because they're over a pretty finite area and frequency, we can possibly bin them out quite well for a lot of stars. So what do we learn from astroseismology? So that could be an entire talk in and of itself, but I just want to mention sort of two things that really are key to astroseismology. So if we look at this power spectrum here, using this sort of solar example here, the two things we're looking at is large frequency separation, shown here as the sort of delta nu, as well as nu max, which is the maximum peak of the frequencies here. And these correspond to physical parameters on the star, such as the mass and the radius and the effective temperature. So from astroseismology, we can derive fundamental parameters about our star, which you'll see in the other talks is really key to then learning about and pinning down the fundamental parameters for our planet. But I would really encourage you to go ahead and take a look at these papers I've put up here to learn a lot more about the astroseismology. The main takeaway that I want to get for you here is that the pressure mode oscillations, or the P modes, are excited by convection. For our sun, there's a sort of 5-minute solar oscillation. That's the area where it kind of rings at that frequency. These individual modes can live for a few days on the sun, and the net effect is a few meters per second. And this is for our sun, and when we're looking at radial velocities, it dominates over the granulation in terms of the amplitude, but because it's over that more finite frequency, we can bin it out much more easily. And the net effect, just like the convection, is going to change when we look at cooler stars or evolved stars. It's going to change in more or less the same sort of fashion, where it decreases for cooler stars and increases for hotter stars and for evolved stars. But for this effect, we can most likely just fine-tune our observations and minimize it, at least to the 10 centimeter per second level. If you want to go sub 10 centimeters per second, we may be looking at a new ball game. But let's go back to this big global picture here of the convection again. Okay, so we've got convection. What happens now if we have a patch of increased magnetic field? Well, the magnetic field suppresses the convection. It kind of takes a bite out of the convection. And if we have enough magnetic field, then we're going to inhibit the heat transport so much that we'll end up with a cooler area. And that's when you get these star spots. I'm showing you here a really cool movie of actual solar observations where you can see a sunspot. The dark region is the umbra, and then that brighter region that you see here is the penumbra. And then you've got your sort of quiet sun or regular convection going on the outside. And you can see from looking at this video that there are extra velocity flows that I don't have time to talk about here, but if you want to check them out, I'd say to go ahead and look up about Mote flows and Evershed flows. But the main takeaway here is that the magnetic fields, when you have strong enough magnetic fields and there's enough of them grouped together, you're going to inhibit that convection. If you don't have a strong enough field to inhibit the convection so much that you end up with a cooler area, what we end up instead is actually a brighter region, because you have the magnetic fields and they are once you get a strong enough field, then the flux tube evacuates and the opacity changes. So that means the magnetic field is really just allowing you to see deeper into the star, and deeper into the star is hotter. And so what you're looking at tends to be sort of the granular walls or the granular tops. Or sometimes if you're very much at decenter, you have those magnetic bright points I mentioned before, where you're really just seeing direct on. But these bright regions are mostly termed Faculae or Plage. And you can see them here associated both next to the spots in this image of the sun, as well as on their own. And they're a lot more spatially diffuse than the spots. And you can think of Faculae as the sort of individual brightenings. So I'm showing you 3 different images of the sun here in different filters. In the G band, which is more like your visible band here in green, the little bright features that you're seeing in between the granules, you can think of those as the Faculae. And you can all think of the Plage as possibly that chromospheric counterpart. So if you remember, the chromosphere is the next level up, and you can probe that by looking at the calcium H and K. And Annalise Montier and Jen Bird will talk more in detail about how we can use the calcium H and K to probe the stellar variability. And one of the reasons why is because it really probes these magnetic features, and you can see it here where we can see the Plage being illustrated. So overall, I've discussed this change in brightness. So how does that impact our line profiles? So let's take this example here where I'm showing you this cartoon where you have the star. So because the star is rotating towards us, just rotating on its own axis, the bit that's coming towards us is blue shifted, and the bit that's coming away from us is red shifted. And if you put a patch of a dark area there, then you're going to block out some of that blue shifted or red shifted light. And in the end, that means you're going to change the net velocity shift. So you can look at it here where you have this example of a cross correlation function or a line profile. We have flux on the y-axis and velocity on the x-axis. And that dark region where you have less light looks essentially like an emission bump here. And you can see you've got this funky asymmetry now because of the brightness difference. So if you were to go ahead and try to measure the velocity of this line, chances are you're going to get the center of light wrong, and you're going to measure a sphere's velocity. Now, in addition to that, in addition to the asymmetry change from the brightness, there's asymmetry changes because you've changed the convection. And there's also a net redshift because you've suppressed those blue shifted granules. And so you get both a photometric effect and a suppression of convective blue shift effect. So again, bringing us back to this global picture, you can see here, you can compare the Plage and the spots in this example that I mentioned earlier. You can see how much bigger the Plage are in terms of the spatial coverage that they have, as well as how they appear both with the spots and on their own. And the spots on our sun tend to appear in particular latitude bands. We deem them active latitudes. And there's some evidence that we can see this on other stars as well. So the takeaways, again, are that Faculae or Plage are bright and they have high magnetic fields, and you're seeing deeper into the star in those regions because the opacity has been altered. Whereas spots, they appear dark because the convection has been so inhibited that you actually have a lot less heat transport there, and it's cooler, and there's a lot of velocity flows going on with those as well. And if you have a pore, that's kind of like a small spot and it doesn't have a penumbra, it doesn't have that extra ring around it. But the key here is that both alter the brightness and both suppress the convection. And because they are on the surface of the star and they're pretty large inhomogeneities, the radial velocity effect is tied to the stellar rotation. For the effects like granulation and oscillations, those are happening sort of almost somewhat the same all over the star. They're inhomogeneities, but they're spread out pretty homogeneously. Whereas you could see those plage and those spots have particular regions. And so if you see a spot and it rotates in and out of view, then you're going to get a signal in your radial velocity that's tied to the stellar rotation. And the spots for our sun and the sun-like stars tend to have a similar lifetime to that stellar rotation. For the sun, we're looking at about 27 days, but the plage can survive several rotations and therefore have lifetimes of a few months or more. And the contrast that you get between the bright and the dark regions of the plage or the spots compared to the quiet sun, that contrast decreases for cooler stars. So you will have a smaller amplitude in your RV effect if you were to measure the same type of spot on an M star as compared to a G star. For our sun, the net effect from the photometric side of things for spots and plage is a few meters per second, but the spots can be a much larger effect if you're going to more active stars. Usually they tend to be younger stars rotating very fast, and you can have up to 100 meters per second or more in terms of just spot variability. And there's a lot of literature that has shown times where we've said, oh, we think there's a planet here, and someone has written a paper and said it was a planet with particular mass and so on, but in the end it turned out to actually just be a star spot. So that was a lesson we kind of had to learn very early on, is to make sure we study and look at this stellar variability and we're not confusing planetary and stellar signals here. But the dominant effect for a sun is not the photometric effect, and it's not the spots. It's actually the plage, because it's linked to the suppression of convective blue shift. So both the spots and the plage have that suppression, but because the plage are brighter, that means it impacts our radial velocities more. And you can have, over the course of a solar cycle, about 10 meters per second variability from the plage alone. And that's something I'll touch on again later in this talk. So our spots, you might have guessed, will be modulated by the magnetic activity cycle, as will all of our stellar variability. What I'm showing you here is the classic solar butterfly diagram. So you have latitude on the y-axis and the date in years on the x-axis. So you can see several solar cycles here, where an individual solar cycle is about 11 years, and then the polarity is reversed, and then you get another 11 years. So you can think of it as either 11 or 22 years. And you'll see that the spots start out at a particular latitude, and then as you go over your magnetic activity cycle, they change in latitude. And then as the polarity is being reversed, it changes in latitude again here. And that has to do with the meridional flows as well, and how they're being modulated over the solar cycle. So it's important to keep that in mind. That naturally brings us to, what does the velocity effect look like over a solar cycle or a stellar cycle? Well, I'm showing you here some velocities derived from our sun. So you've got velocity on the y-axis up to 12 meters per second, and day on the x-axis, where you're covering a solar cycle here. And this is where you get that 10 meters per second variation that I'm talking about. And this is primarily driven by the change in the net convective blue shift over a solar cycle. And to put this into perspective, let's remind ourselves, what does a true Earth twin really look like? Well, this is that 9 centimeter per second signal here, overlaid up here at the 12 meter per second level here. You can see that these wobbles are incredibly tiny compared to the variations over the solar cycle. And so just from the solar cycle changing, it would be very difficult to pull out what an Earth twin signal would look like and be able to disentangle that. In addition, it's also going to be hard to find these longer period planets. For example, Jupiter has an orbital period around the same length as our solar cycle. And if we were trying to observe the solar system from afar, it'd be quite difficult to pull out and disentangle Jupiter from the magnetic activity cycle. So we need to be able to have different indicators that tell us what the stellar surface is doing. And for that, I'll direct you again to the talks by Annelies Matier and Jen Bird. So the takeaways here is the time scale is around a couple of decades or a decade or so. And we're still trying to figure out exactly how this works on other stars and what dynamos are operating on other stars. But this kind of gives you an idea about the amplitudes that we're looking at, which are running around 10 meters per second. And it's really important to keep in mind that any stellar variability that is related to the magnetic field is going to be modulated over this activity cycle. And that net increase in the magnetic field increases the suppression of the convective blue shift. And that's really the dominating factor for sun-like stars. There are a variety of other different smaller scale sources of stellar variability that I haven't had time to mention here. Things like flares and coronal mass ejections, where you can see them in this movie in the bottom left-hand corner here. But because those happen over shorter periods of time, we typically tend to just clip them out. But maybe our clipping out is not perfect, or maybe in the future, if you want to find planets around stars that flare a lot, you're really going to need to possibly take care of that. And those meridional flows that I've mentioned, illustrated here on the right-hand side, those also have a net velocity effect on them. And those active regions have inflows and outflows we could possibly care about. And there are Rossby waves on the surface of our sun that have oscillations around on the meter per second scale on time scales of 10 to 20 days. So that's another source we could end up having to care about. In addition to the fact that if you have a star of a given mass and it changes radius, for example, maybe because the convective properties changed over your solar cycle, if you have a change in radius, then you're going to end up having a different gravitational potential energy if your mass is the same. And then that means your gravitational redshift will be different, which would result in a wholesale velocity shift with no potential counterpart in terms of the asymmetries. Because as you will see in the talks by Jen Bird and Annelies Matier, the asymmetries in the line can be key to diagnosing what sort of stellar variability is present, in addition to other activity indicators like the calcium or what's happening in the H-alpha lines. And so this one could be a little bit tricky. Fortunately, the scale that we're looking at is probably 5 centimeters per second or lower. So it's not our biggest problem to worry about. And we really need to tackle the other problems first. And there are probably other sources of stellar variability that I haven't mentioned here. And as we continue to improve the resolution and the precision of our spectrographs, then we're going to need to have more and more knowledge of the stellar physics, because all those little subtle features are going to be resolved and going to have effects in our data. So it's really important that we understand the stellar physics to a high level in order to be able to disentangle and pull out the planets. So there are a whole load of really great talks coming up this week. And if you are someone tuning in later and looking at these talks from the Sagan Workshop on YouTube, I'd really encourage you to check out all of these other talks here, especially the whole week, but really these ones here have a lot of crossover with the talk I've talked to you, the talk that I've mentioned here. And in particular, again, these are the ones that I've been highlighting throughout, what we can learn from the sun and the techniques to mitigate the stellar variability from Annelies and Jen. But I'd also like to point out this EPRV initiative that Scott Gowdy is going to talk about. And the EPRV, what that stands for is Extreme Precision Radial Velocity. So what we've done with the EPRV initiative is we've come up with a global group of people to kind of develop a roadmap and say, okay, here is where we are in terms of what we know about the sun and sun-like stars, and here is where the instruments are. What do we need to do to improve our knowledge and improve our instruments to get to that sub 10 centimeter per second level to really make sure that we can pull out a true sort of Earth twin in the future? And Scott will talk about the ideas that we have for that But I want to also highlight here as a concluding, these are some of the various physical effects that I've mentioned today. And now I'm going to highlight them based on different color coding. And this is something we came up with in the EPRV initiative, where the red and the darker orange are really the areas that we need to invest in terms of the research and time and money and people power. We really need to understand the sun because it's the best target, the best laboratory for us to study this variability and figure out how we apply this to stellar physics. And we really need to improve our knowledge of the sort of fundamentals, how the line profiles are formed and how they behave in the stellar atmosphere. And I mentioned many times throughout here the Faculae and the Plage, and that suppression of the convective blue shift being the dominant source of radial velocity variability from the star itself. So those are the first things we need to tackle. But intertwined in all of that is the magnetic fields and the granulation and all these other effects that we really need to look at too. So here's if you haven't been paying attention or you've fallen asleep, here's the real key take-home message for you. The interplay between convection and magnetic fields drives most, if not all, of the stellar surface variability. And that completely swamps the Doppler wobble from a low mass, long period planet. Again, this plot you've seen a few times here, this was shown in yellow earlier, but now I'm showing you here in gray. This is the variability from our sun overplotted with an Earth analog. The variability from the star itself is completely swamping that Earth twin. And even if you're not looking for exactly an Earth twin, you just want a temperate, rocky planet around a sun-like star, you're still going to really need to understand the star if you want to pull that out. So the takeaway is convection, magnetic fields. We need to understand that interplay in the physics governing the stellar surface if we want to unveil rocky, temperate alien worlds in the future. So thank you very much for your time. If you're following the Sagan workshop in 2020, I look forward to discussing with you in the future with the live talk and the panel talk. And feel free to go ahead and put some chats in the Slack channel. And in the future, if you're looking at this, go ahead and don't be shy. Send me an email if you have some questions. I'd love to hear from you. And I can't wait to discuss more, and happy planet hunting. Thanks.